So, dear students, um, take down this problem. Our next example with a series of point loads traveling from left to right of this beam 30 meter span. Hmm. So, the question is to find maximum negative shear force and positive shear force and bending moment at 9 meter from the left end. From the left end A. Okay. And also calculate absolute bending moment value. Also calculate absolute bending moment value. So consider this load case. So it comprising of 4 point loads and one UDL continuously traveling with the fixed distances. So keep in mind the distance is 1 meter, 1.5, 1.5, 2 and 4. You have to familiar with these distances because then only you find comfortable with solving further. Okay, for our convenience, we have to take this is W1, W2, W3 and W4 and the loading is W5. So totally 4 point loads and one UDL is there. First we can start. So what are the, we can revise the procedure for maximum negative shear force as well as positive shear force. For negative shear force, place the head and we have to shift one load to the right. Where for the positive shear force, place the tail on the section and we have to move one by one in the left direction to find out the SI ratio. SI ratio WC by L minus WI. WI is the load which is moved uh, away from the section, that is the critical load. C is the spacing between the load moved away from the section and the load placed on the section. L is the span, capital W is the total load. Okay, then maximum bending moment at a section needs LR ratio WL by X minus WR by L minus X. We have to compare the sign convention in the consecutive trials. When the sign changes, the load which moved at that particular trial is considered to be critical load. Then we have to place the critical load at the section and calculate the bending moment under the section. So in maximum shear forces, if it is positive value, we have to move for another trial. If it is negative value, we have to consider the previous one and we can start calculating the shear force at the particular section. So maximum negative shear force, first of all. So our section is 9 meter, so that the remaining distance is 21 meter. So we have to calculate RB. I'm going to first place the head. Head means this is the head position because the load is traveling from left to right, I said. So head and tail position. So place the first load so that the next load will place accordingly. And you compare the distances 1, 1.5, 1.5. So totally 4, 6 plus 4, totally 10 meter span is required, but we have only 9 meter on the left side. So some portion of the UDL will be away from the support. So the distance is, here it is 2 meter, 2 or 3, this is 1, this is 1.5, this is 1.5, so totally 3 4, here 2, 6 and 3 meter. Here in this edge it is 3 meter, 1 meter away from the support. So we place the load. Next, make some convenient table, that is load position at the section. So which load is going to be placed at the section? First one, W1 is here, no? So next trial, we are going to move W1 to the right of the section so that W2 is on the section. W2 means this 100 kilonewton. So the first trial itself, the load position is W2, that is 100 kilonewton load. Why we are mentioned with W1, W2 means some of the loads are repeated, 200s are there. So we have to mention whether it is W1 or W4. First load is W1, second is W2 and so on. So the load position, okay. And the C distance, you can make the C distance, the value. If you move the first load on this, that is 50 kilonewton load on the right of the section, so that 100 kilonewton is on the section and further 150 and 100 and the total UDL will be placed because to compare the distances 1 meter, 1.5, 1.5, 2, totally 5 plus the UDL span is 4. Totally 9 meter is accommodated perfectly. All loads came inside. So this is the diagrammatic representation for the first trial. So the C distance is the load moved to the right is 50 kilonewton and the load placed on the section is 100 kilonewton. So the distance between these two is equal to C. So 1 meter distance. Okay. Then the formula, we will have SI equal to WC by L minus WI. The total W equal to add up all the loads 50, 100, 150 and 100 and UDL you should not add 10 kilonewton per meter. You should add total load 10 into 4 here. 10 into 4 here. So 150 plus 50, 200, 300 and 400. 440 is the total load, capital W. Okay. Now we can calculate 440 into the C distance 1 divided by 30 minus WI is 50. Minus WI is 50. So you need to calculate this value whether it is positive or negative. I think you have calculated the value. I got 35.33. So you can have additional column as remarks for our convenience. So the sign is minus, hence the shear force decreases. The negative sign in this formula indicated the shear decrement. So we should not consider this case. We should not consider this movement of 50 kilonewton on the right side. We should place the 50 kilonewton as in the case of previous. So in this case is right. So the shear force decreases. Hence the W1, that is 50 kilonewton, should be placed over the section. Placed over the section. So this is our conclusion. Our trial has been finished with one time. So I am going to place the load. So this diagram you can use. Mark the section 9 meter, 21 meter. Place 50 kilonewton and next load 3, 4, fourth load and some portion of UDL will be beyond the section. This span is 3. Here it is 2 meter, 1.5, 1.5 and 1 meter. Okay. So you clearly specify the distances and I am going to mark loads 100, 150 and 100 and 10 kilonewton per meter. That's all. Once the load is placed, then it is an ordinary analysis. Here, maximum negative shear force asked. So you have to calculate only RB value, not the RA value. You need not specify RA here. You can specify the support A because you're directly going to calculate RB because RB is the negative shear force. So RB into 30. I'm going to put minus RB because of the actual sign convention. We have followed that. This is the positive sign convention. So the section right side will be here upward, but the positive sign convention is downward. So I put minus RB into 30 so that other loads are to be positive because this rotation is like this. All other loads are rotated about A in opposite direction while taking moment about A equal to 0 to find RB. So I put minus RB into 30 so that all other loads are positive. 50 into 9 plus 100 into 9 minus 1 because we need this perpendicular distance. So it is totally 9. If you deduct 1 meter, that will be the perpendicular distance. Plus 50 into, if you deduct 8, 8 is this perpendicular distance. If you deduct further 1.5, 6.5. Okay, 6.5 plus 1.5 is 8. So 150 into the particular distance, 6.5. Further, 100 into another, we have to deduct 1.5. So 5. Overall, 1, 2, 3, 4 loads are accommodated and plus 10 is the UDL and the loaded distance. Loaded distance is only 3. Okay, 3 square by 2. You should not take into consideration this portion. This portion should not be considered. So the only loaded length is 3. So 10 into 3 square by 2 equal to 0. You please calculate the RB value. I'm also going to check with the calculator. So the value is minus 92.33 kilonewton. Okay. Then this is our shear force. The RB value will not be the shear force in many cases. We have to confirm that there should not any load in this space to directly have RB as the shear force. If there is some load here, we have to deduct the particular load to calculate the shear force up to this section. In our case, we have considered this load position so that there is no load in this span. Okay, so directly this is the shear force at 9 meter from left support. So negative shear force. Next one, maximum positive shear force. So positive shear force means it is always RA and mark the section 9 meter, 21 meter. So all the loads possibly to place on the right side. So first trial I am placing UDL. The first, the last load, that is the tail of the load should be placed here. So first one is UDL 10 kilonewton per meter. The second, third, fourth, fifth. Actually, this is W1 50 kilonewton and next 100 kilonewton. 150 kilonewton and 100 kilonewton. So in this case also, this is W1, W2. We should not change the order every time. The first load is always 50 kilonewton. The last load is the UDL. Even though the tail is placed here, we should not change the order of the loading. So the possible movement is the UDL. Move the UDL on the left side, place the fourth load, place W4 on the section. Okay, we mark some load position. Next C distance. Next SI ratio. WC by L minus WI and remarks. It is your convenient to make this table. It will be very useful to judge the position. Okay, now I am going to shift this UDL on the left side so that the next load 100 kilonewton on the section, further 150, further 100, next 150. So this is the new placement. Okay, 10 kilonewton per meter. So the distance between the point load and the UDL, you make some centroidal distance here because it is 4 meters span. The total UDL is 4 meters. So I am making at the center, making this section at center. So this is 2 meter already given. The centroidal distance will be 2 meter, totally 4 meter. C is 4 meter distance. The load position is W4 on the section. W4 means 100 kilonewton on the section. Okay. C distance is 4. SI equal to total load already we have calculated 440 into 4 by 30. The load which moved on left side is the total load. It is an UDL actually. It is an UDL. So the load is 10 into 4. We have to consider total magnitude of the load, not as 10 kilonewton per meter. 10 into 4 is the load quantity. Okay, you calculate this value whether we can check whether it is positive or negative. Okay, I got positive value 18.67 kilonewton. It is increasing trend. It shows increasing trend of shear force. We can move on to next trial also. So in the next trial, this is the section 9 meter. Already 100 kilonewton is on the section. So I moved the 100 kilonewton on left so that 150 kilonewton on the section towards left side. The UDL already is there 10 kilonewton per meter. Okay, place other loads, that is 50 and 100 kilonewton load is specified here, 50 kilonewton, 100 kilonewton. Actually, why we are moving the load on left side instead of right? Because the vehicle is moving from left to right. And we are considering some tail portion here so that all the loads on its front. So there is no meaning of moving this load in this direction further. There is no meaning. If we want a trial, we have to shift one load on the left direction only in maximum negative shear force. In maximum positive shear force. In maximum negative shear force, if you see, we are placing the head so that the tail is in front. So the possible movement is only to the right side, not to the left side. If you move a load to the left side, it is meaningless. So in negative shear force calculation, you should try to move a load on right side. In maximum positive shear force calculation, you have to move one load on the left side. So in the second trial, we moved two loads so that the W3 is located on the section. So in the second case, W3, that is 150 kilonewton on the section. On this section, you make the table conveniently spacious, and now the distance between the moved load and the placed load is actually this is 1.5, here 1.5. So this is 1.5 meter. 1.5, 1.5, 2 and 4 meter. This is actual distances. So 1.5 is the C distance. 1.5 is the C distance. So SI ratio 440 into 1.5 by 30 minus which load is moved? 100 kilonewton load is moved. So minus 100. Minus 100. Then this value is minus 78. Please check. I have already calculated minus 78. So it decreases. In remarks, you write it decreases. So the movement is wrong. This movement is wrong. We have to consider the previous movement, which will give the maximum value. If the value is in negative sign, it indicates that shear force decreases. So we have to consider the previous one. Which is the previous one? First of all, this is very first position. This is first trial, and here it is second trial. This second trial failed. So we have to consider the first trial. So you make the same diagram for RA calculation. Okay, this is our section. Place 100 kilonewton here, and next 150, next 100, and next 50 kilonewton. Okay, so that the UDL is here 10 kilonewton per meter. So 4 meter distance, 2 meter, 1.5 meter, 1.5 meter, 1 meter, 1 meter. You mark the support here. This is maximum positive shear force at 9 meter from support A. So I am interested in calculating only RA. So how we can calculate taking moment about B equal to 0, we can have the values. Before that, we have to mark all the possible distances so that it will be easier. So 9 meter. You calculate this is 3 plus 1, 4. So 21, 21 minus 4. 17, 17 and 4, I think. 17, 18 plus 3, 21. Okay, this is 17 meter, the edge distance. Okay, now we can write the moment equation about B equal to 0. So rotate all the forces about B. So now RA is the positive sign convention component. So RA into 30. And all loads are in opposite direction only. This is in this direction. RA is the opposite direction. So we can put negative sign for all loads. So 50 into 17, the edge distance, if it is 21, this is 17, minus 100 into 17 plus 1. So this is 17 plus 1, that is 18, plus 150 into 18 plus 1.5, 19.5, plus 100 into again 1.5, 21, 21. Okay. Next one, plus 10 into 4 is the total UDL, and the centroidal distance is from center of the loading to this. Center of the loading to this. You can have 21 here plus 2, 23 plus 2, 25. Whatever may be the way of deciding the centroidal distance, you can have in any one of the side. So now you calculate RA value. You calculate RA value. Actually, I put negative in, I put positive instead of negative. So, because RA is positive, so you put R negative sign here. Equal to 0. Put equal to 0 because MB equal to 0. So I got RA equal to 289.17 kilometer. So now please note that our RA value is 289.17. Our section is here 9 meter. Remaining distance is 21 meter. The loading case here is the section load is 100 kilometer. The load on the section. Remaining loads are placed here. I am not interested on that side. 10 kilometer per meter. Now, what is the value of shear force at XX? Because our question is to find out the maximum positive shear force at the given section, that is at 9 meter from the left side. So, we have to calculate the shear force here. In this case, you observe RA is there and one loading is there. So we can't write RA equal to the shear force up to the section because one more load is there. So shear force at XX equal to RA minus 10 into 4. So 289 minus 40. So that 249.17 249.17 kilonewton. Very important point to be noted is we have to check every time whether there is some load in the span or it is fully clear so that RA or RB is directly the shear force at that particular section. Okay. Next one, maximum bending moment at 9 meter from support A. Okay. Okay, I'm going to draw some approximate representation 9 meter and 21 meter. I'm going to represent all the loads. I'm going to hang the loads here because I don't know exactly where to place it. So 50, 100, 150 and 100. We have to make a trial, that is load position or critical load. You can mention as critical load because which load affects the LR ratio. Next one WL, next one WR, next one LR ratio. LR ratio equal to WL by X minus WR by L minus X, where X is equal to this distance and L minus X is equal to this distance. So I am going to trial that keeping 100 kilonewton per meter on the left side and all other loads on the right side in my first trial. Okay. So the load, critical load here is W5. I can write W5. That is 100 kilonewton per meter I took. So WL is the total load on the left side of the section. So 10 into 4 is the total load. So that the right side load, if you add up all the loads 50, 100, 150 and 100, total it is 400. Okay. So LR ratio equal to 40 by 9 minus 400 by 21. So in remarks, you can mention positive or negative. Please calculate. I got minus 14.60. Next, I'm going for another trial. Place 9 meter and 21 meter distances, and I shifted two loads on the left side. One is 10 kilonewton per meter, another one is 100 kilonewton. All three other loads are on the other side, 50, 100 and 150. So in this time, the critical load is W4. W4, which is 100 kilonewton. Okay. Left side load is already 40. Now 100 is added. So 140. Right side load 200. 200, 300. Right side load 300. So LR ratio equal to 140 by 9 minus 300 by 21. Please calculate. I got 1.26 plus, because sign is very important, 1.27 as answer. So the sign changes from negative to positive. It is changed because of this critical load W4. So W4 is the critical load. So we have to place this critical load on the section and calculate the bending moment under the load. This is the concept. So you can write the sign changes from negative to positive. So W4, that is 100 kilonewton, is the critical load. And mention the condition. Place the critical load on the section and find the bending moment. So I am drawing the beam and the section 9 meter. I am going to place this critical load 100 kilonewton so that UDL on the left side, further loads 50, 100 and 150. Okay, and mark all the remaining distances. Here totally 21 meter, 9 meter, here 2 meter, 4 meter. So if you deduct 4, 2 from 9, it is 3 meter, 1.5, 1.5, so 3, 4 and 17 meter. Okay, if you deduct the remaining distance is 17 meter. Actually, for this case, we have calculated positive shear force. Maximum positive shear force. The same load is placed at this section and I have calculated the RE value. You can use this value for the maximum bending moment procedure, because the placement of load is same in this case as well as in the previous case. So you can use this value RA for the particular calculation. No need to again calculate. So RA value is 289.17, 289.17 kilonewton. RA. You need not calculate RB because the bending moment value can be calculated from each side. Either you can take a A or B. So now I have RA value. So I am going to use from A side up to the section XX. So write down the bending moment at XX is equal to RA into 9. RA into 9, only this UDL is to be added because there is no other load. Minus 10 into 4 is the load and the center of gravity up to the section. So this is the distance. So 2 meter here and the center of the UDL is 2 meter. So totally 4. So this is the bending moment value. So 289.17 into 9 minus 40 into 4. Calculate the bending moment value, which is 244.53 kilonewton meter. Please check. Okay. So this is all about maximum bending moment at the given section. Next one, absolute maximum bending moment. For this category, we have to calculate the resultant force for the given loading. So this is 10 kilonewton per meter, 4 meter, 2 meter, 1.5 meter, and 1.5 meter, 1 meter. I am assuming, we can assume anywhere in between this span, the resultant, because we don't know the distance. Only thing R is equal to total load. We know the total load equal to 440 kilonewton. So I'm going to mention 50, 100, 150 and 100 kilonewton. Okay. Then taking moment about this point, moment of forces, taking moment of forces, because we are taking moment for the forces. So taking all the forces rotating about this axis. So all the forces rotating in this direction, only R is rotating in the opposite direction. So 50 is the first load. The distance is overall distance, that is 4 plus 2, 6, 3, 9 and 1, 10. So 50 into 10 plus 100 into 9, because this distance is 9 meter, plus 150 into 7.5, I think. 7.5 plus 1.5 equal to 9. Okay. Plus 100 into 6. 100 into 6. Okay. Plus 10 into 4 into 2 minus the resultant. We have to include the resultant because we should know the distance for the resultant force only, where R equal to 440. With this equation, find out x. X equal 7.28 meter from left side, because this is very important. Which side you have considered the x? You have considered the x from left side. Now you judge where the load, where the resultant will be placed. So this is 4 meter. Here it is 2 meter. So it passes 6 meter distance. If you add 1.5 here, it will exceed 7.28, because it totally 7.5 meter from this left side. So in between these two only, the resultant will be located. So approximately I am drawing, that is 7.2 meter to 8 meter from this. Okay, and this is 10 kilonewton per meter. Here it is 100 and 150. Okay, and now you consider this item separately. If you deduct 6, if you deduct 7.28 minus 6, 1.28 is the distance. The distance between the 100 kilonewton and the resultant are equal to 1.28, because already 6 meter which is included. If you deduct 7.28 minus 6, which is 1.28, and the next load I am going to locate, which is 150, the total distance is 1.5. So 1.5. So the distance on left side is larger than the remaining distance on the right side. That is 1.5 minus 1.28. Only it is 0.22 meter. So which is very near to the resultant, whether 100 kilonewton or 150 kilonewton. The distance on right side is very less compared to the left side. So this 150 kilonewton is nearer to the resultant. So this 150 kilonewton is the critical load. This 150 kilonewton is the critical load. What is the condition? The critical load and the resultant should be placed equal distance from the center. So how we can place equally? I am going to divide in this figure itself. 0.22 is to be divided into half. So 0.11 should be this distance. So I am going to draw a beam over here. Okay, so that the center point is here. So that the center point is here, and 150 is located, 100 located, and here one UDL. Further, 100 kilonewton and 50 kilonewton is here. So the loads are located. Now you delete this resultant because the resultant is only the opposite reaction. We should not consider in our calculation. So our center of the beam fixed and 150 is also fixed. The all other loads 100 kilonewton and remaining loads all are placed accordingly. 1 meter, the distance here is 2 meter, 4 meter, and this is the center point. Okay, this is the center point. What is the central distance? It is 15 meter. So you add all the distance, that is here 0.11, 1.28. Actually, slightly this figure is confusing little bit. Okay, next page we will present clearly. Okay, this is the center point. So this total distance should be equal to 15. So you deduct to get the edge distances because our calculation needs the edge distance value multiplying for bending moment value. So I am going to calculate this distance as totally 15 minus this 0.11, 0.11 and this 1.28. Okay, and the next this 2 minus 2 and 4, this 4. So you will get the edge distance. So 15 minus, I slightly modified this diagram for better understanding. Actually, we found that 7.28 meter on the left side. So if you deduct 4 and 2, you will get clear distance from 100 to resultant, that is 1.28 meter. 1.28 meter, that is the distance between 100 kilonewton and the resultant. Okay. Totally 100 kilonewton and 150 kilonewton will be 1.5 meter. Okay, 1.5 minus 1.28 will be 0.22 meter. We already calculated is 0.22 meter. That's why we considered 150 kilonewton is the critical load, which is nearer to the resultant than this load. So 0.22 is to be divided into 2. The condition is the critical load and the resultant should be placed equal distance from the center. So 0.22 by 2 is 0.11. So I locate the center at this point. So I made a vertical line to indicate 15 meter, that is midpoint. And if you place 0.11 from the center, if you place 150 kilonewton load at 0.11 meter, then 100 can automatically be placed and 50 also can be placed. From 150 to minus 1.5, 100 can also be placed. So all the loads, if only one load can able to place in the beam, means all other loads can also be placed. So the only thing is we have to mention all the distances. That is, from the center, the critical load should be at 0.11 and mark all the loads and the distances. So from the 150 left side, 100 kilonewton should be placed for a distance of 1.5 because our 100 and 150 is the spacing between these two loads are 1.5, and the left out load UDL 4 meter span and the between distances is 2 meter. So I need this distance. How we can calculate the centroidal distance? Center of the beam is 15. Okay. minus this 0.11 minus because the resultant distance and the critical load is 0.22. So if you divide it by 2, it is 0.11. So 15 minus 0.11 and this distance is 1.28 minus this 2 and minus this 4. So if you calculate 15 minus 0.11 minus 1.28 minus 2 minus 4, which is equal to 7.61 meter A and B. So the absolute maximum bending moment should be calculated under the critical load after placement. So either we need RA or RB value. So this distance also 15 meter. So we have to mark all the edge distances for our calculation. 15 means again you have 0.11 here and 1.5 and 1. So this distance equal to 15 minus 0.11 minus 1.5 minus 1. 15 minus 0.11 minus 0.15 minus 1. So totally 13.74 meter. So with this, we can find either taking moment about A or B. So I'm going to take moment about A equal to 0. So RB into, we have to find the reactions to calculate the bending moment. RB into 30 minus 50 into, we need the whole distance up to A. Okay. How we can calculate? Add all the distances. 4 plus 2 plus 1.5, 1.5, 1. So 3 and 4, 6 and 10. With this, add this distance also up to A. 10 plus 7.61 minus 100. So if it is 17.61, this 1 meter to be deducted because 1.5, 1.53, 5 and 4 is 9. So 9 plus 7.61 and minus 150 again. This is 1 to 1.5 meter, 1.5, 2, totally 3.5, 7.5. 7.5 plus this edge distance 7.61 and the fourth load minus 100 into, this is 2 plus 4, 6, so 6 plus 7.61 minus 10 into, this load is 10 kilonewton per meter, so 10 into 4, the center order distance of the load is 2 meter and the edge distance is 7.61. 2 plus 7.61 equal to 0. We calculate RB value. I got the answer. RB is equal to 218.45 kilonewton. So we proceed with the RB side. We need the bending moment under the critical load. Our 150 kilonewton is the critical load. So RB into this distance minus this load, two loads and their consecutive perpendicular distances will give the absolute maximum bending moment. So absolute maximum bending moment equal to, I am considering RB as negative because of the negative sign convention, minus RB into the distance between RB to the critical load is 1.5 plus 1 plus 13.74. So 2.5 plus 13.74 plus, when you consider RB as negative, automatically the loads are positive. 50 into 2.5 plus 100 into 1.5 equal to, I got 3272.628 kilonewton meter. So you can compare this absolute value will be definitely higher than the maximum bending moment under any possible locations. So I think you will be able to you are able to understand this problem. You can go some more problem in the next video for further understand. Thank you.